Welcome to Math Zone African Motives. Today, we're diving into Unit 4.2, Algebraic Graphs. Our focus will be on a fascinating curve known as the rectangular hyperbola. By the end of this lesson, you will be able to define and describe a rectangular hyperbola, list its key features, and accurately sketch its graph based on a given equation. This means you'll be able to understand the basic characteristics of this type of graph and create your own sketches. First, let's establish our foundation. We'll be working with a specific type of hyperbola called a rectangular hyperbola. Remember, you pronounce hyperbola as hyperbola. Let's begin by defining the form and shape of our hyperbola. This is essential for understanding how to sketch it. The general form of the equation for a rectangular hyperbola is x times y equals k, where k represents any constant number. The constant k plays a crucial role in determining how the graph looks. Specifically, its sign tells us the shape and position of the hyperbola's parts. The hyperbola is a unique graph because it is always made up of two separate parts, called branches. The first rule is, if the constant k is a positive number, the branches of the hyperbola will always be drawn in the first and third quadrants of the Cartesian plane. Conversely, if the constant k is a negative number, the branches of the hyperbola will be located in the second and fourth quadrants. This gives us a very powerful shortcut. By just looking at the sign of k, we immediately know which quadrants to sketch our graph in. Remember that a positive k means first and third quadrants, and a negative k means second and fourth quadrants. Now, let's explore a very important concept called asymptotes. This term describes a key feature of our rectangular hyperbola. An asymptote is a straight line that a curve approaches infinitely closely but never actually touches. Think of it as a target line the graph is always aiming for, getting closer and closer forever. The rectangular hyperbola is an asymptotic graph. This means that its two branches will approach the x-axis and the y-axis, but they will never intersect them. The axes are the asymptotes for this graph. Understanding asymptotes is crucial for sketching. It tells us the boundaries for our graph and how its branches behave. They get infinitely close to the axes but never cross. So, never draw a branch of a rectangular hyperbola that touches or crosses the x or y-axis. The general form with a positive k, so xy equals k, will have one branch in the first quadrant and another in the third. Notice how each branch bends towards the axis, getting closer and closer. For the general form with a negative k, xy equals minus k, the branches are in the second and fourth quadrants. The principle is the same. They approach the x and y axes without ever making contact. Beyond its shape and position, the rectangular hyperbola has several key mathematical features we should understand. Let's look at them one by one. First, for both the positive and negative forms, the graph is a function. This means for every x value, there is only one corresponding y value. Second, it is a discontinuous graph. This is because it has a break, a jump, at x equals 0. The graph isn't a single continuous curve. Now for symmetry, a beautiful property of this graph. The graph is symmetrical about two lines, y equals x and y equals minus x. If you were to fold the graph along either of these lines, the two branches would align perfectly. This is a very useful property for sketching. For the domain, we need to ask what x values are allowed in the equation. Since we can't divide by 0, and x and y are multiplied, neither can be 0. The domain is the set of all real numbers except x equals 0. Similarly, the range asks for the possible y values. Because y also cannot be 0, the range is the set of all real numbers except y equals 0. So we've identified the domain and the range, and they both exclude 0. Finally, an interesting feature. This graph has an inverse function, and its inverse is the same as the original function. If you swap x and y and xy equals k, you get x equals k, which is the exact same equation. The graph is its own mirror image across the line y equals x. Now, let's put our knowledge into practice. We'll work through the first example from the textbook. The problem asks us to sketch on separate systems of axes the graph of x times y equals 8. Let's break down the solution step by step. Remember, the general form is xy equals k. The first step is to identify the constant k. In our equation, xy equals 8. The constant k is positive 8. Because k is positive, we know the graph will be in the first and third quadrants. The constant 8 is positive, which means the graph will be in the first and third quadrants. To get a more accurate sketch, it's a good idea to find a few points. We can do this by rewriting the equation as y equals 8 over x. Let's create a table of values for a few x values. This will give us a better idea of the curve's shape. If x is 1, y is 8. If x is 2, y is 4. If x is 4, y is 2. And if x is 8, y is 1. We now have 4 key points in the first quadrant. Now we can plot these points on a coordinate plane. Plot the points 1, 8, 2, 4, 4, 2, and 8, 1. Remember, the asymptotes are the x and y axes. Now sketch a smooth curve through these points, making sure it approaches the axes but never touches them. The branch should look like the one in figure 421. The solution in the textbook is correct, but let's take it a step further. We can find the corresponding points for the third quadrant using symmetry. If xy is a point on the graph, then so is xy. So the points in the third quadrant will be 1 to 8, 2 to 4, and so on. We can then sketch the second branch through these points. Remember to label the entire curve as xy equals 8. And that's the complete graph of xy equals 8, with both branches correctly placed. Excellent. Now, let's move on to the second part of example 410, which involves a negative constant. This time, the problem asks us to sketch the graph of x times y equals negative 9. Let's follow the same systematic approach. Our objective is to draw this graph accurately. First, we identify our constant k. In this equation, k is negative 9. Since k is negative, we immediately know that the branches of our hyperbola will be in the second and fourth quadrants. So the graph will be in the second and fourth quadrants. This is our primary guide for sketching. Let's find some points to make our sketch precise. We can rearrange the equation to y equals negative 9 over x. We'll build a table of values for a few x values to find corresponding points. This helps us visualize the curve. Let's choose some convenient x values. If x is 1, y is 9. If x is 3, y is 3. And if x is 9, y is 1. These points will all be in the fourth quadrant. Now, let's plot these points on our coordinate axes. Plot the points 1, 9, 3, 3, and 9, 1. Remember that the asymptotes are the x and y axes. Sketch a smooth curve through these points, making sure it gets very close to the axes but never touches them. This corresponds to the branch in figure 422. Again, the textbook solution is correct, but let's complete our sketch by finding the branch in the second quadrant. We'll use symmetry again. We can find points in the second quadrant by taking the opposite of the x values we used before. If x is 1, y is 9. If x is 3, y is 3. If x is 9, y is 1. We now plot these points. After plotting these new points, sketch the second branch in the second quadrant, approaching the axes. Label the entire curve as xy equals negative 9. You have now successfully sketched the complete graph. Let's quickly compare our results with the textbook solution. This is always a good practice to ensure understanding. For the first example, xy equals 8. The textbook correctly states that the constant 8 is positive, meaning the graph is in the first and third quadrants. Figure 4.21 shows this accurately. Our complete sketch, which included the third quadrant, is the full representation of this graph. For the second example, xy equals negative 9, the textbook correctly states that the constant negative 9 is negative, so the graph is in the second and fourth quadrants. Figure 4.22 illustrates this correctly. Again, our comprehensive sketch, showing both branches, completes the picture. In both cases, our analysis and sketches align perfectly with the principles established earlier. The textbook memo is correct and provides a solid foundation. To recap, we have learned to identify the sign of the constant k in the equation xy equals k, which tells us the quadrants. We've seen that the graph has asymptotes at the x and y axes, and we can find points to create a precise sketch using symmetry to complete the graph. You have now learned how to define, describe, and sketch a rectangular hyperbola. Thank you for watching this tutorial from Math Zone African Motives. Subscribe for more tutorials on various mathematical topics. Let's work through one more example to solidify our understanding of sketching rectangular hyperbolas. For this example, let's sketch the graph of xy equals 12. We will follow the same steps we have established. Let's begin by analyzing the constant. First, we identify our constant k. In this case, xy equals 12, so k is 12. Since k is a positive number, we know that our graph will have its branches in the first and third quadrants. So we are sketching a graph with two branches, one in the first quadrant and one in the third. Next, let's find some points to plot. We can do this by rearranging the equation to y equals 12 over x. Let's create a table of values for a few x values to find points on the curve. For the first quadrant, let's choose x values that are factors of 12. If x is 1, it is 12. If x is 2, y is 6. If x is 3, y is 4. If x is 4, y is 3. And if x is 6, y is 2. These give us a good shape for the first branch. Let's plot these points on our coordinate plane. Remember, our asymptotes are the x and y axes. After plotting these 5 points, sketch a smooth curve that passes through them, bending towards the x and y axes without ever touching them. This is our first branch. To complete the graph, we need the branch in the third quadrant. We can use the symmetry property. For every point x, y on the graph, the point negative x, negative y is also on the graph. Using our points from the first quadrant, we can find the corresponding points in the third. If 1, 12 is on the graph, then so is negative 1, negative 12. If 2, 6 is on the graph, then so is negative 2, negative 6, and so on. Now, plot these points in the third quadrant and sketch the second branch. It should be a mirror image of the first branch, also approaching the x and y asymptotes without touching. Label the complete graph with its equation xy equals 12. Let's work through one more example, this time with a constant that is not an integer. For this example, let's sketch the graph of xy equals 4.5. The process is exactly the same as for integer values. Let's analyze the constant and find points. First, we identify our constant k. Here, k is 4.5. Since 4.5 is a positive number, the branches of our hyperbola will be in the first and third quadrants. So, we'll be sketching a graph in quadrants 1 and 3. Now for the points. Let's rearrange the equation to y equals 4.5 over x. We will create a table of values to find points. It's helpful to choose x values that make the calculation easy. For the first quadrant, let's try some x values. If x is 1, y is 4.5. If x is 2, y is 2.25. If x is 3, y is 1.5. If x is 4.5, y is 1. These points help define our first branch. Now, let's plot these points and sketch the branch in the first quadrant. Remembering the asymptotes are the axes. Plot the points. 1, 4.5. 2, 2.2. 3, 1.5, and 4.51. Sketch a smooth curve through these points, approaching the x and y axes without ever touching them. To complete the graph, we use symmetry to find the points for the third quadrant. The corresponding points in the third quadrant will be 1, 4.5, 2, 2.25, 3, 1.5, and 4.51. Plot these points and sketch the second branch. Label the final graph with its equation, xy equals 4.5. As you can see, the method is robust and works for any non-zero constant k. Let's work through a final example to make sure we are comfortable with the process, this time with a negative constant that is not an integer. For our last example, let's sketch the graph of xy equals negative 6.4. As always, we'll start by analyzing the constant k. This will tell us the location of the graph. Our constant k is negative 6.4. Because k is negative, we know the graph will be in the second and fourth quadrants. So we are looking for two branches, one in quadrant 2 and one in quadrant 4. Now, let's find some points for an accurate sketch. We'll rearrange to y equals negative 6.4 over x. Let's create a table of values for x and y. For the fourth quadrant, we need positive x values. If x is 1, y is 6.4. If x is 2, y is 3.2. If x is 4, y is 1.6. If x is 8, y is 0.8. These points will define our first branch. Now, let's plot these points on our coordinate plane. Remember, the asymptotes are the x and y axes. Plot the points 1 at 6.4, d, 2, 3.2, 4, 1.6, and 8 at 8. Sketch a smooth curve through these points, making sure it approaches the x and y axes. To complete our sketch, we need the branch in the second quadrant. We'll use symmetry to find its points. The corresponding points in the second quadrant will be 1, 6.4, 2, 3.2, 1.6, and 8, 0.8. Plot these points and sketch the second branch in the second quadrant. It should be a symmetric image of the first branch, also approaching the axes. Label your final graph with the equation xy equals negative 6.4, and there you have it, the complete graph. Let's work through one more example, which demonstrates that the rectangular hyperbola doesn't have to be centered at the origin. We'll sketch the graph of xy equals 5. Our task is to sketch the graph of x times y equals 5. We'll apply our familiar two-step method to this problem. First, we identify the constant k. In the equation xy equals 5, k is 5. Since 5 is a positive number, the graph will be in the first and third quadrants. This means our two branches will occupy the first and third parts of the coordinate plane. Now let's find some points to help us sketch the shape of the branches. We'll use the form y equals 5 over x. We need to choose x values that will give us easily plottable y values. For the first quadrant, let's select a few points. If x is 1, y is 5. If x is 2, y is 2.5. If x is 5, y is 1. These 3 points will be sufficient to draw the first branch. Now let's plot these points. Remember, the asymptotes are the x and y axes. This means our curve will get closer to the axes but never touch them. Plot the points 1, 5, 2, 2.5, and 5, 1. Sketch a smooth curve through these 3 points, making sure it gets very close to the x-axis as x gets large, and very close to the y-axis as x approaches 0. This is our first branch in the first quadrant. To complete our sketch, we need the second branch. This branch is in the third quadrant and is symmetrical to the first. The corresponding points in the third quadrant, found by taking the negative of the x and y values, are 1, 5, 2, 2.5, and 5, 1. Plot these points and sketch the second branch, ensuring it mirrors the first branch and approaches the axes. Label the entire graph with its equation, xy equals 5. This is the complete sketch of the rectangular hyperbola. Let's work through one last example to ensure a thorough understanding. We will sketch the graph of xy equals negative 4. We will follow the same methodical approach, starting with the analysis of the constant k. First, we identify our constant k. In the equation xy equals negative 4, k is negative 4. Because 4 is a negative number, we know immediately that the branches of our hyperbola will be in the second and fourth quadrants. This gives us a clear roadmap for where to draw our graph. Now, let's find some points to make our sketch accurate. We'll use the rearranged equation y equals negative 4 over x. It's always best to choose x values that are factors of the constant to avoid difficult fractions for sketching. For the fourth quadrant, we'll choose positive x values. If x is 1, y is negative 4. If x is 2, y is negative 2. If x is 4, y is negative 1. These 3 points give us a good shape for the first branch. Now, let's plot these points on our coordinate axes. The x and y axes are our asymptotes. Plot the points 1, 4, 2, and 4, 1. Sketch a smooth curve through these points that approaches the x and y axes without touching them. This is the first branch of our hyperbola. To complete our sketch, we need the second branch in the second quadrant. We'll use the property of symmetry. Using symmetry, the points in the second quadrant are 1, 4, 2, 2, and 4, 1. Plot these points and sketch the second branch. It should be a mirror image of the first branch, also approaching the axes. Label the entire graph with its equation, xy equals negative 4. Congratulations, you've now sketched a rectangular hyperbola with a negative constant. Let's work through one last example to ensure a thorough understanding. We will sketch the graph of xy equals negative 2.25. Our task is to sketch the graph of x times y equals negative 2.25. We will follow the same methodical approach, starting with the analysis of the constant k. First, we identify our constant k. In the equation xy equals negative 2.25, k is negative 2.25. Because k is negative, we know immediately that the branches of our hyperbola will be in the second and fourth quadrants. This gives us a clear roadmap for where to draw our graph. Now, let's find some points to make our sketch accurate. We'll use the rearranged equation y equals negative 2.25 over x. It's always best to choose x values that make the calculation easy. Here, x values like 0.5, 1, 1.5, and 3 are good choices for the fourth quadrant. For the fourth quadrant, we'll choose positive x values. If x is 0.5, y is 4.5. If x is 1, y is 2.25. If x is 1.5, y is 1.5. If x is 3, y is 0.75. These points help define our first branch. Now, let's plot these points on our coordinate axes. The x and y axes are our asymptotes. Plot the points: 0.5, 4.1, 2.2, 1.5, 1.0, and 3.075. Sketch a smooth curve through these points that approaches the x and y axes without touching them. This is the first branch of our hyperbola. To complete our sketch, we need the second branch in the second quadrant. We'll use the property of symmetry. Using symmetry, the points in the second quadrant are 5, 4, 5, or 1, 2.25, 1, 5, 1, 5, and 3.075. Plot these points and sketch the second branch. It should be a symmetric image of the first branch, also approaching the axes. Label your final graph with the equation xy equals negative 2.25. You are now proficient in sketching rectangular hyperbolas. Let's summarize everything we've learned about rectangular hyperbolas. Mastering these concepts is key to success in algebraic graphing. First, the general form of the equation is x times y equals k, where k is a constant. Second, the sign of k tells us which quadrants the graph will be in. A positive k means the first and third quadrants, and a negative k means the second and fourth quadrants. Third, the x-axis and y-axis are asymptotes. This means the graph approaches them but never touches or crosses them. Finally, the graph has a beautiful symmetry. The two branches are symmetrical about the lines y equals x and y equals minus x. By following these rules and using our two-step process of identifying quadrants and finding a few points, you can accurately sketch any rectangular hyperbola. Thank you for joining this tutorial from Math Zone African Motives. Make sure to subscribe for more tutorials to help you excel in mathematics.